Hey everybody, Dr. A here, and in this video we're going to be exploring a simple example of hydraulic conductivity in soil. So let's go ahead and get started. In the given information, we're being told that a permeable soil layer is underlain by an impervious layer. So what we have here in this diagram is we have the ground surface, and it has a water table at the ground surface. So we can assume that this entire layer is saturated and is permeable. And the impermeable layer is beneath that. So this space under here represents the impermeable layer where we're assuming that water cannot flow. We're given a hydraulic conductivity here of 0.00035 feet per second, and we're being asked to compute the rate of seepage in cubic feet per hour per foot. Okay, so if we look at this diagram again, we see that we have flow occurring from a higher elevation down to a lower elevation. And based on this diagram, we're assuming that this is one-dimensional flow or one-directional flow. So that means that the flow is exclusively occurring along a path that is parallel to the soil layer, okay? The vertical height between the ground surface and the impermeable layer is 10 feet. And the slope of the ground surface, which we can also assume is the slope of the base of the layer, is at a 3-degree angle, okay? So that's what we're looking at. So let's go ahead and get started. When we are being asked to compute the rate of seepage, what we are looking for, if I write solution here, is going to be Q equals KIA, all right? It's that simple. So this is a direct application of Darcy's law. Now, do we have K? Absolutely. This K value that is in Darcy's equation is our 0.00035 feet per second. So if I wanted to check this off, I can put a little check mark there for K. Now, the next two elements of this equation we need are I, which is the hydraulic gradient, and A, which is the cross-section area of flow, okay? So let's remind ourselves how those are defined. I is our hydraulic gradient, and we know that that is a head loss over a flow length. And then A is our cross-section area of flow, all right? Now, the units that the problem is asking us to compute the rate of seepage in is in cubic feet per hour per foot. So we need to remind ourselves, what does that mean? Well, the cubic feet per hour, that's a volume over time, which is the basic units of flow rate Q. But what about this per foot? Okay, we have this cubic feet per hour per foot. What does that mean? Well, the per foot refers to a unit length coming in and out of the screen at you, okay? So think of this soil layer that, is sloping at a 3-degree slope in the plane of the screen, but it extends indefinitely in and out of the screen. And so because we don't know the actual dimension of this soil layer that is out of plane or coming in and out of the screen at us, we're going to perform this calculation on a per foot basis. So again, this per foot is a unit length coming out of the screen or into the screen, okay? So we got to keep that in mind. So how do we do that? Well, if you look at this diagram, it seems like we're not given very much information, all right? Again, we need I and we need A, and we don't really seem to have a whole lot of that information. Let's start with A. How about we just go straight to A? That's the cross-section area of flow. Where is that going to be? Well, I'm going to use my original diagram to help me visualize that, okay? So the cross-section area of flow is going to be an area that is perpendicular to the direction of flow here, okay? So there's a perpendicular segment, and that area A is going to be represented really by this red line here. Okay, now you might be thinking, well, that's a line, not an area. Well, the other dimension of that area is that per foot that's coming out of the screen at us, okay? And so what we're looking at is a distance defined by this red line times 1 foot coming out of the screen at us. So the real work that we have to do here is really just some basic geometry or trigonometry. How do we get this length right here? Well, let's extract that and see if we can do that. So what I'm going to do is I'm going to take this red line and I'm just going to kind of redraw it over here to show my scratch work, okay? So that is this line right here, all right? Now, what do we know already? Well, we were given that height, h, okay? That's 10 feet, all right? And then we also have the boundary of the permeable layer, okay? So somewhere here, we're gonna have a right angle. Where's that gonna be? Well, we have this right angle right here. So we have a right triangle in that case, okay? And so if we have a right triangle and we have a vertical dimension of 10 feet, what can we do with that? Well, the next thing we need to recognize is where this angle alpha is. So in this diagram, alpha is also right here. Alpha is 3 degrees. And so we can do some very basic trigonometry, and we can say that cosine of alpha is going to be equal to, what's the definition of cosine? Well, it's adjacent over hypotenuse, right? So we can say the cosine of alpha is this length right here, okay? And I'm going to call that maybe little l. I'm going to say that that's adjacent over hypotenuse, which is 10 feet. And then I'm going to call that value little l 10 feet cosine alpha. And again, alpha is 3 degrees. And so we can get that L value, again, we say 10 times cosine 3 degrees, and that's, you know, almost 10. That's 9.986 feet, okay? Now, what about A, the area A? Well, we said the other dimension of that area is 1 unit foot coming out of the screen at us, okay? And so we can say that A is L by 1 foot. So we can say that that's 9.986 square feet. Okay, so now we have A. All right, what about I, the hydraulic gradient? That's H over capital L. Well, where is that here on this diagram? We have to do a little bit more trigonometry and define that. So here's what I'm going to do, okay? If you remember your knowledge of fluid mechanics or hydraulics, if we want the head loss, we're going to need some information about an upstream and downstream head. So here's what I'm going to do. I'm going to put some boundaries here arbitrarily, okay? I'm going to put a perpendicular here, and I'm going to put another perpendicular here, okay? Or not really perpendicular, vertical lines, I guess is what I should call that, right? And what I'm going to do is I'm going to say, let's define a little triangle right here, okay? And we're going to call this little vertical dimension here H. We're going to say that's the head loss. So what we're kind of pretending like we're doing is putting 2 piezometers at these 2 spots, okay? And then we're pretending like that the water level in those 2 piezometers, the difference in that is going to be our head loss. That's effectively what we're doing here, okay? And so the next thing I'm going to do is I'm going to look at the length, okay? So what I'm really interested in is this horizontal length right here, okay? I'm going to call that maybe L prime, all right? Now, is that the flow length? Not really, okay? The flow length is actually this length right here, okay? L, all right? And so I'm going to use some similar trigonometry techniques here. I'm going to first look at the right triangle that's defined up here with a vertical height of little h. So that's a right angle there. And again, I know that this interior angle is 3 degrees. And so from that right triangle, what can I do? Well, again, I'm going to use some basic trigonometry here. And I'm going to say h is going to be equal to L prime times tangent of alpha, okay? And again, that's going to be L prime tangent of 3 degrees, all right? Now, what's L prime? Again, that is the horizontal dimension here. So what I'm really doing is saying tangent of 3 degrees equals h over L prime, and do a little bit of rearranging, all right? What about this length L right here, this diagonal length? Well, again, I can look at a little right triangle that's defined by a hypotenuse of regular L, and I can do some basic trigonometry, and I can say that L is equal to L prime divided by cosine of alpha, which again is L prime over cosine of 3 degrees, all right? Now, I know I didn't show all of my triangles and my trig like I did when I did this area calculation, but it's a very similar process, okay? So maybe I encourage you, if you're not convinced of this, pause the video, take a few extra minutes and draw it out yourself and piece it together yourself. Once we get that, we're gonna say I is equal to L prime tangent of 3 degrees, because that's h, that's the numerator, and then the denominator here, which is L, is going to be, we're going to say that's divided by L prime divided by cosine of 3 degrees. And then, of course, we can clearly see that the L primes cancel, and you end up with, let's change colors here to be consistent. You end up with a tangent of 3 degrees multiplied by a cosine of 3 degrees. So what is tangent of something times the cosine of that same something? Well, you know, tangent is defined as sine over cosine. So you can clearly recognize this simplifies down to sine of 3 degrees, okay? And so that's I, right? That is I. And now we can check that off. And so quite simply, we can say Q equals K, which was, I believe, 0.00035 feet per second, 0.00035 feet per second. I simplified down to just sine of 3 degrees, and then A simplified down to 9.986 feet squared, all right? And so what does that come out to be? Let's do some calculations. I'm pulling out my TI-36X Pro, 0.00035 times the sine of 3 degrees multiplied by 9.986. And so I get 0.000183 cubic feet per second. And remember, this was on a per foot basis because we had that unit of 1 foot coming out of the screen at us. So I can also write this as per foot. Now, the problem asks for this in terms of cubic feet per hour per foot, right? So we just have to do a little time conversion. So I'm going to do that here, 0.000183 cubic feet per second per foot. And how do I go from 1/seconds to 1/hours? Hopefully that's pretty easy enough. We can just say we've got 60 minutes. I'm sorry, we've got 60 seconds per minute. So we see that the seconds cancel there, and then we can say multiplied by 60 minutes per hour. And then, of course, we would see that those minutes cancel, and we would finally calculate value of, say, times 60 times 60. So I get 0.659 cubic feet per hour per foot as my final answer of the flow rate. And again, that's per foot coming in and out of the screen at you, so per unit width, okay, or per unit length. So that concludes this example. Again, I encourage you, if you're a little rusty on some of your trig manipulations, pause the video, draw out some triangles, and make sure you can see how I piece together A, L, L prime, and I all together. So if you found this video helpful, please hit like and subscribe, and be on the lookout for other content like this. Thanks for watching.